For 14.6, we added an additional input, car NS, which stands for cars north-south. It's also a sensor in the north-south direction. And we have also is changing the logic just a little bit so that east-west stays green until a car waiting in the north-south direction is detected. We still also have a sensor for the east-west direction as well. So here in our state diagram, a state 0, we have north-south being green and east-west being red. When a car is detected in the east-west direction, so when it's a 1, it goes to state 1, and that's when it starts changing, the lights change colors for north-south from green to red. So here at state 3, east-west is now green, and north-south is red. And it'll loop in state 3 as long as there's no cars detected in the north-south direction. As soon as a car is detected, it'll go from state 3 to state 4. And from there, east-west will now change from green to yellow, and then from yellow to red. And so at state 5, it'll go to state 0, where north-south is now green and east-west is red. So to our code, I created a component for the finite state machine. So we'll go ahead and talk about the top level. I have two inputs, car EW and car north-south. They're basically sensors for both the north-south and east-west direction. And also have a clock and a clear input as well, which will also, these four here will feed into the finite state machine. So for my outputs, I have 6 outputs, which represents the traffic lights. I labeled it in such a way that the first letter is the color of the lights, and the last two is the direction. So R and S is red, north, south, and it will follow the same pattern and so forth. I have a signal that's T lights, which is a standard logic vector. It's 6 bits wide, and that holds the output from my finite state machine. So for my finite state machine, I have the clock and reset, car NS and car EW, which are the sensors for the north, south, and east, west. And my T lights is my output for the traffic lights, and it is a vector that's 6 bits. I have a signal that's CS and NS. They are my current, CS stands for current state and NS is next state. Because I have 5 states, I create a vector that's 3 bits wide. This is my process block for my clock and reset. So basically what this does is if my reset is a 1, then it'll take my, wherever state I'm in, it'll go to state 0. This is my current state. If reset is low, so then it'll follow the rising clock edge, and my next state will update my current state. So in this block here, this process block is detecting my current state, my car north-south, and my car east-west. I created a case statement for the current states to make it easier to navigate. So at state 0, I have my if statement that checks to see if car east-west is high or not. So basically, if the sensor is detecting a car, if it does detect a car, then it will be a 1, and it'll move to the next state to state 1, or else the state is state 0. So the outputs here is 0, 0, 1, 1, 0, 0, and basically it's dictating which lights are on for which direction. So here for it's going to be north, south is green, and east, west is red. So 0, 0, 1, this one right here means that north, south is green, and this one right here is east, west is red. Um, so since as long as a car is detected, it will go ahead and keep moving through the different states. Because traffic lights, as soon as it changes, it will go through the motion based off the rising clock edge. Um, so here, so from state 1, state 2 is we are turning the, I'm sorry, state 1 is the north-south lights are yellow, and in state 1, I'm sorry, state 2, north-south is red, and east-west is red, so therefore no cars are moving. Um, so then it'll go to state 3, and in state 3, if the north-south sensor for car NS is high, then it'll move on to state 4, because that means that there's a car waiting in the north-south direction. Or else, if there is no car there, it will remain in state 3, so therefore east-west will remain green, will be green, and stay green. So if a car is detected at north-south direction, it'll go to state 4. So then, so in state 4 is when the east-west will change from green to yellow. And then it will also go through the motions to change, and once both lights are red, it will cycle back, and from state 5, it cycle back to state 0 for north-south to be green. So in our top level, the reason why I created a vector for my T lights is so that I don't have to, so that it would be easier to not create so many outputs. And since I know which bits in the vector represents the lights, I only care at that certain point, at a certain placement of the bits in the vector where it's high. So here, red north south is my most significant bit in the vector, while green east west is my least significant bit in the vector. So it will follow in that order. In the simulation, to verify that the code is running properly, I had made car north south 0 and car east west 1. So it starts at state 0 because, and I know this because north south is green and east west is red. So it will be that way until the next rising clock edge, where it'll change from state 0 to state 1 because car east west is a 1. And here, to prove that north south is now yellow, has changed from green to yellow. And then in state 3, north south is now red, east west is red, no cars are moving, all stopped. So at the next rising clock edge, east west directions is now green, and north south remains red. As long as car east west or car EW is high, it will remain green and remain in state 3. until we change it to car east-west is 0 and car north-south is now 1. So as soon as a car is detected, it is still in state 3 because east-west is a 1 and, well, east-west green is on and north-south is red. Till the next rising clock edge is when it will register the changes in the sensors. Okay, so at state 4, east-west is now yellow and north-south is still red. In state 5, both lights are now red, as can be seen here. And it'll go cycle back to state 0, in which north-south is now green and east-west is red.